Hi, this is just a math problem. Theta equals L over L plus KD. So theta equals L over L plus KD. And they want you to compare this. It says in the hint, it says, well, there, it doesn't say hint actually. Extrapolate your knowledge with enzyme kinetics. Okay, so enzyme kinetics, this is our knowledge. The initial rate is equal to Vmax times the substrate concentration over the Michaelis-Menten constant plus the substrate concentration. Okay. Okay. So they want you to compare these two, and what do they want? Oh yeah, they want you to get theta in terms of Michaelis-Menten factors and terms. So they want theta to be written in terms of enzyme kinetics quantities. All right. So how do we get theta in terms of theta as a function of enzyme substrate complex concentration, or V naught, or Vmax, or K negative 1, or K1, or K2, etc. How do we get theta as a function of those things? Well, the first thing you do is you write down the Michaelis-Menten equation, just like I've done over here, and then you notice, oh my God, look, this looks a lot like this, the denominator. And you're like, huh, actually, if I write theta again, and I put the L up here, but then I switch the order since addition is commutative, like this, right? Then you're like, huh, it looks like the S is the L. I mean, does that make sense in biochemistry? And you're like, yeah, because with protein and ligand binding, you get protein ligand. And that is the same as enzyme plus substrate binding. You get enzyme substrate complex, and then you get enzyme end product, but that's kind of besides the point. The point is that this is the same. L and S are really the same thing. So all I'm missing is Vmax. Okay, so if all I'm missing is Vmax, how can I make this Michaelis-Menten equation look just like this theta? Or how can I make this theta look just like the Michaelis-Menten? Either way, what I need to do is put a Vmax over here. But see, mathematically, if I put a Vmax over here, that means I have to put a Vmax over here. So it's theta times Vmax equals this. Well, that's no problem, because Vmax times theta equals this. What is this? This is V naught. So put a V naught here, and then we just solve for theta. V naught over Vmax. Is this the only way to solve this problem? No, it isn't the only way. I mean, we could have done it this way. We could have said, let's get rid of the Vmax, so divide Vmax on both sides, like this, and oh my God, this looks exactly like theta, so we'll just say this equals theta. There are many different ways to do this. And you could also do this by the process of elimination, because there isn't, I mean, in a biochemistry experiment, if there's a lab component to this class, maybe you've noticed, nobody can measure the enzyme substrate complex concentration. When we derive the Michaelis-Menten equation, we, on purpose, get rid of all ES, so that the only thing in there is E total and S. Actually, E total gets, even E total is eliminated by replacing K2 times E total with Vmax. So nobody can measure ES usually, so that's just ridiculous. So we just eliminate that, and then Kcat over Km. Nobody said that there was a Kcat here in this problem. Most biochemistry textbooks say that in some cases we call it Kcat, some cases we don't. It depends on who the rate determining step is, you know. And here there's K minus 1. In enzyme kinetics, we don't use K minus 1. We use it when we derive the Michaelis-Menten equation, but the whole purpose of having Km here is so that we don't have to deal with k minus 1, k1, and k2 separately. The only two choices that make sense are these two choices. All right? So you can eliminate the top three and then have a 50-50 chance of getting the answer. Or you could do the math, put the equations side by side and make them look like each other.